we're given this reaction. It is C2O2Cl2 plus water, and it produces CO2, HCl, and CO. And if you balance it, you'll find when you have 2 hydrogens on this side, you need 2 on the other side. That gives you 2 chlorines on both sides, 2 carbons on both sides, and 3 oxygens on both sides, so now it's balanced. The question says determine the enthalpy change for the reaction. So this is like the last question where ultimately we're trying to get delta H for the reaction, which should be in kilojoules of energy per mole of reaction. This question, though, is very different in that it doesn't give us information about an experiment where the reaction exchanges energy with the surroundings. Instead, it gives us information about how stable the bonds are. And so what we're going to learn today is I don't have to do an experiment most of the time unless I'm working with substances that aren't really known substances. If I produced a new compound in my research and I want to understand its thermodynamic properties, I would have to do an experiment. But for many substances, I can find ways to calculate energy associated with the reaction they'd be involved in without actually running that reaction. It's mostly what the lecture today focuses on, because it's way easier to do a calculation on paper in 10 or 15 minutes than it is to set up an entire experiment and make sure you've accounted for all the variables and the heat exchange is accounted for and there's no heat loss to the room and things like that. So one way to do that is to focus on the bonds that are breaking, right? Because we know whatever attractions I have to break in my reactants, that is going to absorb energy from the surroundings. Breaking attractions always is accompanied by an increase in potential energy, and that energy has to come from the surroundings. Then when I form new attractions, new bonds, energy is released, because once I break all the attractions, the particles are really unstable and high in potential because they have the potential to come back together. Once they do come back together, they'll be lower in potential, and that difference in potential energy will be released to the surroundings. So I can say that the reaction itself, which is a combination of both attractions breaking and attractions forming, the overall amount of energy associated with that reaction, whether it's releasing energy or absorbing energy, will be dependent upon all the energy required to break the bonds that I have in the reactants being absorbed. So that would be a positive quantity of energy associated with the bonds breaking, which is called bond dissociation energy of the reactants. So I'm going to add those all up. Basically, I'm deciding what's the sum of the amount of energy required to bond dissociate or break all the bonds in the reactants. And then I'm going to subtract from that, because when I form the new bonds, that's going to release energy. And from the system's point of view, releasing energy is always negative. The sum of all the energies released, which is the opposite quantity of energy if they had to be, if those bonds had to be broken for all the products, right? So if I'm breaking bonds, I absorb energy. If I'm forming bonds, I release an equal amount of energy. So I can, for both of these, I can use numbers for how much energy is absorbed when I break a bond, which is what bond dissociation energy is. I just realized it's a negative sign if I'm forming bonds rather than breaking them. So that's the equation I want to use. But I have to be able to draw Lewis structures if I want to know exactly what type and how many of each bond is present. So if I'm given a formula, I need to draw out the Lewis structure. So here, carbon is less electronegative, so it should be my central atom. Connect the 2 carbons together. I've got oxygens and chlorines. I could think about how to connect those. If I put both oxygens on the same atom, it's probably not going to work out, because once I count up the total number of valence electrons and put those in, that would require, so that's all the valence electrons I have, that would require me to share some extra electrons with the carbons to complete their noble gas configurations. But if I share between the chlorine and the carbon a double bond, it's going to create some unnecessary formal charges. So that's not the ideal structure. Plus, when I look at the given information, there's no given information about the bond dissociation energy of a carbon-chlorine double bond. So it's unlikely that I have that in my molecule. If it were in my molecule and it were involved in the reaction, I'd have to know how much energy is associated with breaking that bond, and I don't have that information. So that's a clue that when you draw your Lewis structure, you should probably involve bonds that I actually give you information about in the question. And so that means when you connect the carbons, you've got to put the oxygens on both carbons instead of having both oxygens on one carbon. Then when I put the lone pairs in, I can complete the noble gas for the chlorine without giving it any formal charge. And when I complete the noble gas for the oxygens, I can share a pair each there to complete the noble gas of the carbon and also not create any formal charge. So that should be my Lewis structure for that compound. We know the Lewis structure for water creates a noble gas configuration for the oxygen and the hydrogens. Then the CO2 also has double bonds to fulfill the noble gas configurations. I've got two HCl's, so I'm forming two of those. So I want to draw both of them so I don't lose track of how many of these attractions are breaking and forming. And I have a CO, and when I draw the Lewis structure for that, I will find out that it's a triple bond needed to complete both noble gas configurations. So I realize that since the carbon is no longer connected in the way it was before, also the given information tells me that a CO double bond that's found in CO2 is not the same energy as a typical CO double bond So what I want to say about that is that, just to point out, the numbers that will be given to you are averages. Right? So this method does not give you the exact correct answer. It gives you a very good estimate. Right? Because when I'm breaking hydrogen-oxygen bonds, not every molecule that has an oxygen-hydrogen bond will have the same exact energy associated with that bond. Right? So some OH bonds take more energy or less energy to break a little bit. But they're all pretty close. So the given information is that an OH bond, on average, requires 459 kilojoules per mole of bonds. So I need to figure out what bonds are breaking here, what bonds are forming. So clearly I'm breaking the carbon-chlorine bonds. Those are not there in the product. I'm breaking the carbon-carbon bonds. There's no carbon-carbon bonds in the product. I'm not really breaking the CO double bond because that's there. But since the CO double bond here doesn't have the same energy as this one because of the information given, I really need to treat it as if these have to break and then these get to form, and the difference will be accounted for if I do it that way. Alright, so then I want to account for all the bonds breaking and all the bonds forming, which in this case is pretty much all the bonds. So I've got to add that all up. So I want to add up the sum of all the bonds breaking, because that is what absorbs energy and will require the system to have a positive change in energy. So I'm breaking 2 of these carbon-chlorine bonds. So that's 2 moles of the carbon-chlorine bond. And that one I don't have a lot of space here, so I'm not writing everything down, but that one was given carbon-chlorine 339. 339 kilojoules per mole of carbon-chlorine bond. I've got to break the carbon-oxygen double bonds here. And a typical carbon-oxygen double bond is 736. So I've got 2 moles of that I've got to break. And each one of those is 736 kilojoules per mole of CO. I've also got to break 2 OH bonds. 2 moles of OH. And that one was given to me as 459 kilojoules per mole of OH bonds. So that is all the energy that needs to be absorbed to break all the bonds that are there. I'll need to subtract from that the quantity of energy released when the new bonds form. And so I'm forming 2 CO double bonds that are a CO, part of a CO2 carbon dioxide molecule. And so those ones have 799. So I'm forming 2 of those. So that's 799 kilojoules per mole of CO double bond. I also will release, right, so I've got this negative sign here because all of these energies sum up to account for how much energy is released. They're all involved forming bonds. I'm forming 2 HCl bonds, and that's given as 431, 2 moles of HCl bonds, and that's 431 kilojoules per mole HCl. And also, when I do a mole of reaction, I form 1 CO triple bond and that has an energy of 259 or 258. Right, so I'm canceling out all these moles of bonds, and actually probably I shouldn't have left this out, but really what we're saying here is that I don't really have, like, say for example, looking at the carbon chlorine, I really don't have 2 carbon chlorine bonds, right? I have 2 carbon chlorine bonds every time I do 1 mole of reaction. If I do a mole of reaction, I have 2 moles of carbon chlorine bonds. So that's really a relationship. I should have put that in there. So really, this part of the relationship is 2 moles of bond per every 1 mole of reaction. So that should be here under all these, because I'm counting up the number of bonds that need to break or form every time I do a mole of reaction. I want to do a better job of keeping track of my units. So that means when I'm canceling moles of substance, what I'm left with are units of kilojoules per mole of reaction, which is what I want my answer to be, the unit I want my answer to have. So I'm going to get rid of this now, and I'm going to continue this calculation up here. So I'm going to take everything in this first bracket, carry that through in my calculator. So I've got 2 times 339 plus 2 times 736 plus 2 times 459, and that is since all my moles of bonds canceled and all those numbers in kilojoules per mole of reaction, that number 3068 is kilojoules per mole of reaction, and that's the quantity of energy absorbed. That's the total sum of all the energy required to break all the bonds in the reactants. So I subtract from that the total in the other parenthesis, which is 2 times 799 plus 2 times 431 plus 258. And that comes out to be 2,718 kilojoules per mole of reaction. So I can't subtract and add until the units are the same, which they are now since the moles of bonds canceled and they're all per mole of reaction. So then I just subtract that. And I get 350 kilojoules per mole of reaction. And it's positive because that means that more energy is required to break the bonds in the reactants than I get released when the bonds form in the products.
So the amount of energy for every single bond would
Yes, if I give you an example like this, which I probably most likely will, if you're drawing a Lewis structure and you've got bonds in your Lewis structure and I haven't given you information about the energy associated with those bonds, you should probably ask me during the exam to make sure that I didn't make a mistake. But assuming I didn't make a mistake and that information wasn't necessary, that means your Lewis structure wasn't drawn correctly. So if I expect you to do a problem like this, I've got to give you all the information. So I have to tell you the bond association energies for every type of bond that's present that would have to break or form. Now it's possible that this example is not the case, but it's possible that if you draw your Lewis structures and you find that some of the bonds that were there are still there in the end, you wouldn't need to know necessarily the bond association energy for that. Because you only need to know how much energy it takes to break the bonds that actually need to break and how much energy is released when the bonds form subsequent to that, and those are the energies that you would compare.
the only thing you have to cancel there are the number of moles.
Right. Yeah, the moles.
The first one had 2 CCl1, that's why it's like 2.
Right. So when these numbers are given, they're given per mole of that type of bond, not per mole of reaction. In the end, I need delta H that I'm calculating to be per mole of reaction. So I've got to cancel the mole of bonds and get it in terms of mole of reaction. So that's what this conversion factor is for. So if I have a number that's given that tells me how much energy is associated with some of these bonds, that tells me the energy associated per mole of that type of bond. So I need a relationship between how many moles of that type of bond are there in a mole of reaction. That way the mole of bonds cancel and all my numbers are per mole of reaction, so I can actually add them together.